Welcome back, everybody, to day 2 of this workshop. Before we get started, I just wanted to share the Google Doc that we're using, just talk about a thing or two here. So thank you to everybody who took the daily survey yesterday. If you haven't taken the daily survey for Tuesday, if you scroll down to the surveys and take the Nixie Tuesday daily survey, appreciate all the feedback you gave us on that, and we'll be looking to integrate some of that feedback today. And I did post a preliminary recording of yesterday under the links here that isn't cleaned up yet to a point where it's ready to be shared publicly yet. So if you can just use that link for your own reviewing of things and not share it yet, I'll share a public link once that's available. Just like yesterday, we'll be following the Exceed Code of Conduct and terminology statement. So if you have any concerns about that, you can review my slides from yesterday. Let us know if you have any concerns. We went ahead and pulled out the Excel formulas that we used yesterday from the Zoom chat. I put them into the Google Doc in case you want to go back over those. And the Excel workbooks that you'll be downloading are linked in a couple places. One of them is here on the Google Doc, but also as Dr. Panoff goes through the presentation today on the HTML and or Google slide pages, we'll have those linked as well. So that's all I wanted to mention here at the beginning. I'm going to go ahead and stop sharing now, and I will turn it over to Dr. Panoff.
Thank you. Looks like we recovered a majority of the participants from yesterday, and that's a good sign. I'm glad to see you all again. We're going to start with a little bit of review of what we did yesterday, and then proceed to go through some of the newer features of it, not newer features of Excel, but features of Excel you may not be familiar with, or if you are, it's a good reminder. We'll also be sharing some web resources that would allow you to use other people's efforts to convert what we've done in Excel into Google Sheets. So rather than my going through that today, we'll provide a link to that whole tutorial and set of materials for that for Google Sheets. That'll be hopefully helpful to you as we go on. So as we talked about what we did yesterday, we're really trying to use Excel or spreadsheets in general as a computational thinking sandbox. It's a place where you don't have to teach a lot of procedural code. You can get in there, and in one cell, you can teach them how to simulate flipping a coin or rolling a dice or throwing a dart. And then you can use those rudimentary skills to build up other types of things. And today we're going to do more complicated models. What we talked about yesterday in terms of computational thinking is pulling together the application, the algorithm, and the architecture to basically understand simple approaches to computation and to generate a real set of thinking skills. A big piece of what we're doing is multiple representations, helping people form multiple representations. And a big part of that the sandbox that spreadsheets enable is that you can explore different algorithms. You can see what you would get if. But at the same time, you have to be understanding the computational thinking of what's there and what's different. Some people have called computing as being a thought amplifier. Yesterday, we talked about different types of calculators that were online. You can have an exact copy of the Windows calculator that was ported by MIT. There's Google using it as a calculator. And of course, Wolfram Alpha is a good resource for that. One of the things I will urge you to be careful of with Wolfram Alpha is that there are bugs in which they don't necessarily check their work. And they also think that their own data sources are superior to anything external to Wolfram. So if you want to hear my rant on that, check out the previous webinar. I'll be glad to repeat the rant if anybody provokes me. So these were what I promised yesterday would be the ultimate deliverable of this workshop, is to demonstrate and not necessarily convince you, but to at least show you that it's possible to cover all of the basic concepts of what's called CS0, or in some schools, Computer Science 101, or the Introduction to Computer Thinking, in which you have variables, assignments, understanding the difference between a numerical and an algebraic representation. What's the impact of formatting on your interpretation of what comes on the screen? How you can check what's really happening, creating that kind of stimulus for the thinking. The students tend to believe whatever they have on the screen, and they're not very good at the expectation, observation, reflection cycle, which is the scientific method. So you'll notice yesterday, a lot of times when I was presenting something, I would ask you, what would you expect would happen if we did this? What would you expect would happen if we did that? And continuing that line of thought, we'll try to do that. We used a math library to generate a random number, and then showed how different models that are based on randomness could be implemented in various degrees. We also did some things with conditions and branching. We did polling. We showed how you could check a coin, whether it's heads or tails, and then raise your hand, and then count all the hands that are raised up. That's what I call brute force polling. But we also used a math call library to count the number of things in the operation there. We had just a very simple Boolean operator. Today, what we're going to cover is iteration, recursion, color as a numeral, and then go into system and agent modelings and point out where they could be used for stimulating parallel thinking. So we had our simple pet model. We did sort of looking at things for algebra, arithmetic, and numerics. We did some things on randomness. And so what I'll ask is, are there any questions, comments, or concerns about what we did yesterday? Just hit the pause bar or type something in chat. I will point out that we had a slight misunderstanding, at least as far as I can tell, that what I did is I went back and modified my copy of the spreadsheet so that when we were flipping coins, somebody asked that we label the column coins. And so this first one is not actually a coin that's being flipped. You know, it's you can label things different ways. And what I said was that because we're now labeling the top column, the sum is not the sum of everybody, but, you know, it's just going to be the number ones that are there. And if you wanted to count the number of things that were in there, you would have to subtract one. Right? So the sum is still all the ones. Heads equal 1 is not a number, so it doesn't change anything. count if it will count the number of heads in the same basic idea. And so you can do that counting and things yourself. The same with mom. I put in a list there for mom and dad. And then the number of items is whatever in column mom minus 1. Then the COUNTIF is recessive. We actually, now that I look at it, we don't need the -1 because the word child would not be recessive. So therefore it wouldn't show up in the count. So what I'll do is I'll post my version of all of the working copies of things that we did yesterday. And by the end of today, I'll post my copy, or we'll put it in the Google Doc for this Excel example for what we're doing and how we're doing it. Okay. Any other questions, comments, or concerns? Now, what I'm going to do is we're going to start today by looking at the concept of recursion and iteration. Another way it's often described is you have a function that's circular. I mean, one of the things that really messed up people's minds was when they invented early versions of BASIC and Fortran, and you would say, let A equal A plus B, or A equals A plus B. And A was on both sides of the equation, and it just messed up people's minds in the early 60s for how this could be done, because if A is on both sides of the equation, how do you know which one is the new value or the old value? And it took a while for people to get the convention down that it was actually the new value is the old value plus the change in the value. And we'll talk about that later when we do system modeling. That's basically an Euler model. A equals A plus B. The old value of A plus the change gives you the new value of A. So what we want to talk about right now is things that are involved using Excel as a sandbox to explore recursion iteration. To do that, we're going to use variable names. We'll talk about assignment and operators. We'll talk about iteration and the requirement that we change the mode of calculation of Excel from automatic calculation, where constantly Excel is checking every cell all the time to check to see what's there. And if anything changes, it changes the whole spreadsheet. We'll talk about conditions and branching and introduce color as a numeral. Now, to do this, what I'm going to recommend, because changing the calculational mode will mess up other worksheets that you have, there's two types of preferences or options. One are things that once you set the preference, like the developer checkbox, then that's true for all subsequent worksheets that you open. There are other options, which we'll show you today, which are true for that workbook being open. So what I'm doing is I'm closing this workbook, and then I'm going to open a new Excel workbook because I want it to be sort of a clean copy of things that are going on. Now, let's talk about a simple iterative example. And I'm going to start by setting up the example on my iPad, if I have it connected. Let me get it so that it's actually clicked in. Suppose I wanted, now this is going to be interactive. I'm going to need you to unmute yourself and contribute to the answer, and don't let other people intimidate you. Go ahead and say that. Suppose I wanted to solve the equation x equals the square root of x plus 7.312. My first question to you is, how many different ways can you think of solving for x? Who can think of different ways of solving for x? Or who can think of one way to solve for x?
You could square both sides and then use quadratic formula.
Good. Can somebody think of another way of?
Somebody put Punnett squares on, or Punnett square, I think, on both sides. I don't know. There's a comment in the chat.
A comment in the chat. Squaring both sides. I see that. Is there a second method someone could recommend? Well, without delaying too long, and I know it's a little harder in the Zoom, is what if we had a graph of y equals x, and we had a graph of y equals the square root of x plus 7.312. What do you know about this point right here?
It's a solution.
It's a solution because it covers both sides of the equation.
Should have
So,
thought about that. Just taught my daughter how to do that.
so graphing, and in fact, for many, many years, for more complicated equations in physics like Chebyshev coefficients and cubics and quartics, graphing and interpolating off a graph was typically a way that they would find solutions to the problems, even without a computer, so to speak. But this is, so you graph and you look for the intersection. Okay. Can somebody think of a third way to do this?
If you made them both equations, you can add them or subtract them. Like if you make that or that y equals x and y equals x or square root of x plus 7, whatever, there is ways to add or subtract.
Yeah, but ultimately you're going to end up doing a squaring of both sides, even if it's two separate equations. What I'm thinking is something similar to the graphing, and that is, what if you made a table, and going down the table you had a column of x's, and going down the table you had a column of the square root of x plus 7.312. At one point, one of those, just like on the graph, one of those is going to be above the other, and at some point they're going to switch. And what do you know about the row or the rows near where it goes from one side is bigger than the other side is bigger? What if you had a row where they were exactly the same? You would have found a solution, right?
Yes.
So that's another way of doing it is, and then you can expand the table near those rows where it switches, where one side is bigger than the other, and you can get a second, third, fourth decimal place and going through there. So you can make a table and look for the row that has the same value on both sides of the equation. Can you think of another one, which is my students' seemingly favorite way to do things?
Google it.
Well, I hadn't thought of that as actually a method, but you're right. You could Google it and it'll pull up Wolfram Alpha or it'll solve it for you. So I'll put that down here. How about a fifth way of doing it then? I'll give you a hint. It starts with a G and rhymes with mess and heck.
No idea.
Guess and check.
Oh,
You
Yeah.
stick in a number and see if it works. If it doesn't work, you stick in a different number. I mean, I've had students that when I was teaching, I would ask a question and they would shout out different things, and then I would try to be as stoic as possible. And they would just wait until I smiled or something, but they're looking for the reaction. They were looking for you to tell them they got the right answer. But just sticking in a number and seeing if it works, sticking in a number, seeing it works. Those are all, methods. So guess and check. But there's another method that is a real enhancement of guess and check. And that is you start with some value of X and you stick it in the other side, add 7.312, take the square root of it, and then take that value and use it as your next guess for X. And then you take that value of X and stick it in the right side of the equation, add 7.312, take the square root, and then use that as your next value of X. And this is using X on both sides of the equation, which if you look at my gross diagram here, might remind you of a circular calculation. Now, the problem with this, it's not really a problem. The challenge of this with Excel is that if I call this X, and I'm going to call this the square root of X plus 7.312. Well, let me get rid of that underline. So I'm using a math call called squirt, which is the square root. So suppose I said, well, what if it was 0? Then I could come over here and say this is equal to the square root of that cell plus 7.312. And I get a first value. Then I come over here and say this cell is equal to this cell. Now, what would you expect is going to happen from your usual experience of using Excel when I hit the Enter key?
an error message.
It says there are one or more circular, do you see my little pop-up message here?
We see it.
There are one or more circular references where a formula refers to its own cell. This might cause them. And it tells you to remove or change these references. But what we're going to do, and again, if you don't do that, you're going to get this ugly blue arrow that says this whole thing is circular and it's not going to work. Instead, what we're going to do is we're going to turn Excel into an iterative machine. And the way we do that is on a Mac, you go up to Excel and pull down preferences. On a PC, you go to File and pull down Options. Can you see my preferences window?
Yes.
Yes.
Then if you type on calculation, the first thing you do is you change it from automatic calculation to manual. So it will only calculate when you tell it to. Then you come down and tell it to use iterative calculation, where each calculation will do one iteration. So instead of automatic, where it's constantly checking, what we do instead is on a Mac, if you hit Command equals, it will calculate the spreadsheet once. Do you remember that from yesterday?
Yes.
And then on a PC, you will hit F9. Now, in the old days, there used to be something where when you moused over it, it told you that. Maybe it's still true on some versions of Excel, but if you didn't know that, I'd be hard pressed to tell how you would figure out how to do that. So we're going to calculate manual iterative. Did everyone on Macs and PCs get that? All right. So now we're going to do it again. We're going to say, I'll start with a guess of 0. I'll then take the square root of that cell plus 7.312. By the way, does anybody know what the value of X should end up being? Anybody have a guess of what our value of X that solves both sides will be? Okay, just wanted to check in case we had some deep insight. Now, when you do that, the 0 goes over here. Now, I'm going to hit Command equals, or if I was a PC, I'd hit F9. And now I have to come over here and say, this side is equal to that side. And what it did was it took the value here and put it over there. Now, if I hit Command equals, it will take 2.7, add 7.312 to it, gets a number bigger than 9, and it gives you an answer bigger than 3. When I hit Command equals again, the 3.16 goes to the left side, and then the number that was there gets added to 7.312, and you take the square root. And what can you notice, or do you notice anything as I repetitively hit Command equals?
The change gets smaller.
And eventually, does it look like it converges? And if I wanted to, I could take these two cells and format those cells to be a number with 16 decimal places. And you'll notice that at 16 decimal places, it didn't really converge yet. Now it has. And it's telling me that it's approximately 3.25, 3.249909. And did you see the iteration taking place as I hit Command equals 1 point at a time?
Yes.
Yes.
Now, the question I have to you is, what reason do you have to believe this? When I asked you earlier if anybody happened to know what the answer would be, nobody seemed to know what the answer was. So now we have an answer, but why should you believe it? So what I'm going to do is I'm going to suggest what some people call a test case or a test script. Suppose I took this number and made it 6. Okay, so I'm going to take this number and make it 6. And now I'm going to repeat the calculation until it converges. What do you guess it's converging it to? Let's check it. What's 3 plus 6?
9,
What's the square root of 9?
3.
So now we have a value which even us in our poor caffeine-addled minds can do in our head. And so we've tested it on a case where we know that it cannot not be true. What if we came up here and made this number 20? Can you think of a number that when I add it to 20 and take the square root, I'll get back the same number?
5.
So we could try multiple test cases and get the idea that as we're doing this, for all the cases where we know the answer, our algorithm works. And that gives us a reason to believe that when we go back and put in a number that we don't know the answer to, that we will get an answer that we can trust. And that's an important part that I left off that list of programming concepts, which is the concept of a test case or a test script. So this is an iterative method. It gives you the ability of taking a single cell that depends on another cell, but that cell depends on this cell. So this cell uses what's in column A, and column A depends upon column B. And so you can solve other more complicated things as long as you have a convergent algorithm where in the picture, it's like you're zooming in around the intersection point of the two curves. Any questions about that? Now, iteration is one of those things, and the idea of the manual calculation is something which people, from my experience, and especially students, had no concept was actually inside Excel, and has been there since at least 25 years. But you have to turn it on using the options or preferences, because the normal thing is that Excel is constantly checking every cell, and if one cell changes, it recalculates the whole spreadsheet. In the old days, about 8 years ago, the version of Excel that was being well, actually it's longer than that now, 12 years ago, the version of Excel that was being distributed used to include neighbor tables. They used to include tables of which cells actually had something in it, so that when you updated a cell, it would check all the cells that were already populated. You also had an Excel that had a limited number of rows and a limited number of columns. In one direction, you could have 32,000, but it could only be one direction. And if you had 32,000 in one direction, you could only have 255 in the other direction. So it made it computationally compact. With the newer versions of Excel, no neighbor tables, and all bets are off on the size of how many rows and how many columns. If you use your cursor and keep going, you just keep getting more and more columns or more and more rows. And it's substantially slowed down the performance of Excel. So, but for what we're doing for these simple problems, by being able to add iteration to the list of methods that a student could use to solve a problem and understand the concept of convergence, I think this is a powerful example. It's really simple, but it gets across the point of changing an option to give you something better. Now, let me go back and explain what we did and why we did it. Under the options or preferences, if we were to save this spreadsheet, this specific workbook, when we reopened it, would automatically still be manual. That's why I asked you to close the other workbook and open this one, because what often happens is students will start a new calculation in a new workbook with a worksheet already opened that had manual set as a preference, and they won't understand why something isn't updating. The other is I specifically chose to use one iteration per command equals. But, if we had used 100, it would zip through 100 times and it would stop when it got to a maximum change of 0.01. So let me show you that. What the effect, if you didn't make it 1 and do the hitting of F9 or command equals yourself, let me show you what effect that would have had on this problem. So I'm going to come up and do $30. I'll make 30 the additive constant. What do you think it's going to converge to?
Six.
Okay, let's try that. Now, if I hit command equals, it will go through 100 iterations per time I hit command equals. And so it takes fewer hits of F9 or command equals because each time it's doing it, it's doing that iteration 100 times. But it's also stopping and only doing a few because if the change between the two sides is less than 0.001, then it doesn't really give you that. So now we'll come back here and we'll do 42. I'm trying to make sure I type out the expression that I'm using. And do you notice that when I made the change very, very small and I hit command equals once, it immediately converged to 7? Or if I put in a 20 here, I hit command equals once. So what you're seeing is that depending on how you set those parameters in your options/preferences, if you want to be pedagogical, my recommendation is that you go to the preferences or options and make the maximum number of iterations 1. And then it won't matter what you have for this maximum change because it will actually do it every time you tell it. It's very obedient. Now, if you want to be able to save stuff, you'll notice I unclicked recalculate the workbook before saving. That way, whatever you had at your last use of the web, then that could be there. Now, if we wanted to, we could have done the same thing we did yesterday with variable names. We could have called this cell X, and then we could have used the square root of X plus this, and then my text version of the equation would be the same as the equation version of the equation. So if I come back here and put 7.312, so I'll pause for a second and ask, are there any questions, comments, or concerns about that 2-cell iteration?
No.
Okay, do they teach iteration as a method anymore?
in higher level classes.
Okay. Can you see where this is a more sophisticated version of guess and check?
Yes.
Okay, so this is kind of a nice addition to a method where you can show students, as I tried to on my iPad, that there are many ways to solve this problem. You could square both sides, you could graph, you could make a table, you could Google it. Actually, if you'll allow me to, if I actually went to Google and said x equals square root of x plus 7.312. Well, the good news is it doesn't give you the answer in one step. But it will. So, not every homework problem is going to get messed up. Okay. So let's talk about a problem that uses iteration and recursion that has two features. One is every cell in a worksheet will be computed independently, but every cell depends upon the values of the cells around it. So we're going to talk about a good example of this, which is called diffusion. And the basic concept of diffusion is solving a difference equation as simply an iterative recursive process that I am the average of my neighbors. So if I'm next to you, I will use your value to calculate my next value, but you'll use my value to calculate your next value. When we do this, we're going to change the geometry of Excel to give us something that looks more like a grid. The thinking human being playing in the sandbox needs to define the relationship of I am the average of my neighbors once. And then by copying down and copying over, you can do that for hundreds or thousands of cells. So the idea of using a computational environment to replace the tedious, repetitious part of doing the same thing over and over and over hundreds or thousands of times. So what I'm going to recommend that you either watch, or if you want to work along with me, I'm going to give myself a new sheet. I'll call it diffusion. And again, I'll post my version of this later. So the first thing I want to do is I want to start more or less in column D, because I'm going to use A and B and C as workspace. And I'm going to highlight all of the columns up to, let's say, Q. So D through Q are highlighted. Then I'm going to come over and put my cursor between columns D and E. And I'm going to slowly reduce the size of D until it looks more like a square rather than a rectangle. And can you see that it did that for these other squares as well? Now I'm going to pump it back up so you can more easily see what's going on. Now this is going to be my grid, and you'll notice that because I'm in the same workbook where I've already made it manual, if I go up and check my preferences, you'll see that even though it's a new worksheet, it's in the same workbook, which means the same preferences are going to be used. Now, let me tell you the story that goes along with this diffusion. And to do that, I'm going to draw a picture, something scientists like to do a lot. When I was in high school, there was a big population increase in Annandale, Virginia. And as a result, the high school had to put in trailers in the parking lot. And the trailers had very thin walls exposed to very cold temperature where it was freezing. If I could spell freezing. Everywhere outside it was freezing. And what they had done was they put a series of heaters on one end of the trailer and pumped out a lot of heat. And that heat would eventually move into the trailer. And the goal is to study how that heat moves through the trailer. We have a source that will be at a constant temperature, but everybody else will be the average of your neighbors. So if you think of your being in the middle, we're only going to use the 4 nearest neighbors, up, down, left, and right. Since the corners are actually farther away, we're not going to use them in our simple approximation. So if I had this cell, this cell, this cell, and this cell, then I would add up the values of the 4 cells and divide by 4. And then the goal is to figure out how the heat transfers into the trailer over time. And we want to use our computer model to ask the question, how long does it take before the rest of the room heats up if you put all the heaters at one end of the room? Then we'll maybe think about other better ways to solve the same problem. So if you imagine taking this graph paper from my iPad and translating that to here, so what we're going to do is to make it absolutely clear what's going on. We're going to leave the top row. We could actually put, we're going to do this in centigrade. So if we took and said the outside world is 0, let's go down here. So that's the temperature outside on the other side of a wall that has virtually no insulation, because Fairfax County, Virginia was so cheap, they wanted the lowest bidder. Now, the goal of playing in the sandbox as a computational thinker is that we're going to create the correct formula once. And then we're going to do what I just did with the zeros and copy it down and copy it over for every other cell. So if I start at this end of the room and say, I am equal to the value above me. Well, let me cheat and start over. I'm going to say it's going to be equal to, open parenthesis, the value to my right, plus the value below me, plus the value to my left. This isn't going to matter because this is actually the wall of the room. And the value above me. And then we're going to take that and divide by 4. Now you'll notice that there was nothing in this cell, nothing in this cell, nothing in this cell, nothing in this cell. So this is a computed value of 0. Now, the other thing we're going to do is we're going to introduce color as a numeral. And now we get into some cultural things and experiential things that students don't always have the same thing. But is there a color that you would normally associate with somebody getting very cold or it being very cold outside?
Blue.
Blue. And what would you associate with a color that's very hot?
Red.
Red.
Okay, so I'm going to click on this one cell, and above on the home menu, I have conditional formatting. And I'm going to make a new rule, which will be a 3-color scale. Now, I want it to depend on the actual temperature, so I'm going to make the actual evaluation of the cell from minimum, midpoint, maximum to be a number. Did everyone see how I did that?
Yes.
Now, this is one of my experiential stories. We had a wonderful young lady, was in the 6th grade. Her parents sent her to workshops at Shodor because she kept getting low grades in science in her school because she would always spot the exception in a true-false question, or she would always challenge the teacher that something that the teacher said always happens didn't always happen. And she was just very, very bright. And she said, Dr. Panoff, now I understand why I always fall asleep in math. I said, why is that? And she said, because it makes me number and number and number. And I have to admit, at the time this happened, I had never thought of the fact that the word number is also the word number. Anyway, this helped me later on because when I solved the New York Times crossword puzzle, the clue will often be number and the answer will be dentist. So let's make the minimum color blue. We'll make the maximum color red. And I don't care what's the middle number. I'm going to make the minimum number 0. I'm going to make the maximum number 80. And I'm not going to make it linear. This isn't the midpoint in the sense of being 40. I'm going to make this logarithmic. So I'll go 0, 10, 80. And that'll spread out the colors farther, and you'll see that in a bit. So if you're following along with me, you should have a 3-color scale. Each of the types is number. My values are 0, 10, and 80. And I have blue, I don't care what color you put in the middle, and red at the end. Now, what will you expect my cell will turn when I hit OK?
Blue.
And it is. Now I have that whole cell correctly defined. Let me double check my formula. It's hard to see, but it's the sum of the numbers, excuse me, divided by the number of numbers. And now what I'm going to do is I'm going to take that cell and copy it down along the wall and copy it over inside the trailer. Now, did you see any complaining? Did you see any whining? Because we turned off automatic calculation and made it iterative, even though every single cell inside the trailer depends upon the 4 up, down, left, and right values around it. And those values depend on your value. It's completely recursive, but it doesn't matter because it's not going to calculate until we hit Command equals or F9. Now, what I'm going to do is I'm going to take this first cell and put it at 70 degrees Celsius. Did you notice that it just turned red? Now I'm going to take that cell and build the situation I told you we had, which is the design of the trailers, put all the heating elements on one side and the narrow side of the trailer. So I'll pause here for a second and ask the question, does everybody have something that looks substantially similar to mine if you're building it yourself? Or maybe you should tell me if you don't have that, and we should wait until you get to where. Okay, I've got a not yet. And if there's any specific step you think you missed, let me know and I can go back and help you get to where you need to go. Or we can have you share your screen instead of mine and we can diagnose it together.
Okay, I have the red strip of 70s, but what do you do to get the blue? What do you click and drag on?
Okay, so let me. Did you define the very first cell the way we expected and then copy down and copy over?
I didn't copy over.
Well, then you're going to need to undo the 70s and put it back to the formula of the average.
Got it, thanks.
So everybody should be the average of your neighbors except for the cells that are the heating elements. Is there anyone that's not ready for the next thing? Now, normally I would unmute all your speakers here. And I'll do that momentarily. Because I like to hear the reaction to what happens next. If you have everything set up the way we've done it, and I've got my cursor clicked somewhere outside, I'm going to hold down Command equals and watch what happens.
That's cool.
That is very nice.
Did you hear the slight ooh from somebody? Usually we get at least one ooh. Oh, Terry typed in so cool. That's a good thing. So then we could ask the question, do you see how, first of all, color has come a long way. It's no longer, when I was growing up in Washington, D.C. area, we had a television station that used a magnetic board, which a magnetic H and a magnetic L for high and low systems, and then jagged lines for fronts. And now everybody uses color to represent value for temperature, amount of rain, amount of snow. Color is now a numeral. When you see red, you think high number. When you see blue, you think low number. And you'll notice that if about 18 to 20 degrees Celsius is room temperature for that, a large part of the room is way too hot and a large part of the rest of the room is way too cold.
It's not a very good heating system.
Not a very good heating design. Now I'm going to turn the heater off. What I'm going to do is I'm going to click on my spreadsheet in E2 and highlight that column and drag it over to the left so that what used to be 70s are now the average of their neighbors. And now what I'm going to do is let the heater system cool off, and because it's cold outside, watch the moire. Oh, there it goes. Did you see the zeros come?
Yep.
So now we've turned the heater off. So the experiment I'd like to do now is, where would you put the heaters? And they don't all have to be on one wall. But if you put several heaters spread around the room, and then look at the effect of that design, can you see where simulation can lead to better design models? Well, I hit a minus instead of a 0. I keep hitting minus instead of 0. I got a out of control pinky. And now I use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I used actually fewer heating elements than what I had before. And now when I do this, first of all, you see that it's more uniform.
Yes.
And now what I'm going to do is I'm going to define a temperature as the word temp. And then if I had done this better earlier, every place I put the 70 before, I'm going to put a temp. And now I can control the temperature of each of these elements from a single thermostat. And I'm going to do cut and paste rather than typing. Copy, paste, paste, paste. One of the analogies I use is when you play in the sandbox long enough, you actually get pretty good at this. And by setting the thermostat to 40 instead of 70, I can get the whole room to be actually still too hot. Let me make this 35. Watch what happens when I hit 35 and hit enter. Are you ready? And when I hit command equals, every one of the heating elements changed its value to the single value of the temperature. And now I have a design, a heating design. It's not the only one, but you can at least see that it's a much more tolerable set of rooms. Now I can come over here and set it equal to 0 and turn it off during the day. Okay. So hopefully you get the idea that I want to repeat. We used color as a variable, as a numeral to represent a high or low number. We used a single cell to control the temperature of all the heating elements. We could put those heating elements anywhere we want as part of the design. We defined the average of the neighbors once, and we checked it and made sure we really did do left, right, up and down, added up, divided by 4. We copied that column down, lifted up and copied the column over to get the entire rectangular world on the grid paper. We used the ability of adjusting the width of a cell to make it look more like graph paper and more symmetric. We used manual calculation instead of automatic calculation. And by doing that, we were able to do this recursive thing where I use your value, you use my value. And every hit of F9 or command equals gave us one more calculation of where things were going. So let's do a little quiz. I'll show you the thing again. If I turn on, I'll make it 34 this time. So I set the temperature to 34. Why didn't any of the heating elements change their value to 34?
You need to do the command enter thing.
We need to do that at least once. Because it's not automatic calculation. Oops. This. And then if I turn the temperature back off, now there's another skill that's used in this, and that is another type of iterative calculation, which is the idea of a clock. So I'm going to do something using this model to add to it the ability to measure in time how many steps does it take before we converge to a given temperature. Is it clear what we're going to do? So in steps of 1 time unit, and I'm going to call the value of that step, I'm going to have a time. And then I'll have a start. So we haven't started yet. Our time will be the following formula, and I'll write it out here. There'll be an equal sign, but it'll say if start equals 1, then I'm going to be equal to time plus step. Otherwise, I'll be equal to 0. All right, so this is the formula that I'm going to use for time. The difference is there'll be an equal sign in front of it. So if the value of start, which I have to define, by the way, start time. So let me repeat what I've done. I have a variable which is step, and I called it step in the name box. I have a variable called time, and I have a variable called start. The formula is if I've started the heater, I replace the value of time, which is the cell that I'm in, with time plus step. So every time I hit command equals, nothing happens because I haven't started the program. So if I came up here and said this was 34, let's see if we can figure out how long it takes to get to about 20 degrees in the middle here. So I'll make this start equals 1. Question, did you notice that time is now 1, 2, 3, 4? Every time I hit command equals, because start is equal to 1, I replace my previous value with my new value of the time plus the step. And I didn't assign an actual value, but let's pretend the step was in minutes. Then it looks like it takes about an hour to heat up the entire trailer. Now, if I turn off the heat, I could ask the question, does it go back to 0 at about 120? So it looks like cooling and heating are not necessarily symmetric. So it took longer to cool off than it did to heat up. And then if I go back to 0, I'll zero that out there. Okay, it's a good time to take a break. Before we break, I'll ask, are there any questions, comments, or concerns? I mean, often when I do this in class, the students think this is really neat. When I do this with high school teachers, they say, oh, I could use color to mark my grade book. You know, good grades, bad grades could be different colors. When we do it with students, they really get this idea of color visualization. And the physics students can think about torsional bending and pressure differences. The chemistry students can think about the rate of reaction. The biology students can think about hot spots or low spots or temperature in the body. But this idea of I am the average of my neighbors is actually something that occurs across many areas of science. You know, in the old days, I would have a pen, and if I forgot to put the cap on it and it would leak, the ink stain would spread across my shirt. And the closer I am to the ink source, the higher it is, and the farther away it starts to fade out. But it spreads through the nearest crossings of the threads. Any questions on either the original simple 2-cell iteration, the more complex diffusion that uses the same basic idea of iteratively, recursively calculating I am the average of your neighbors? It's a little different equation than the square root equation. And being able to come up with this little model for how you would add a clock or a timer, that you could add step every time you take a step, it would add the value of step to the value of time and give you a new time. And it's hard for me to tell if there's any questions or comments, you can either unmute or raise your hand or. Okay, Aaron, I think we should take a break. My computer says it's 4:18. So how about 4:25, 7 minutes from now? I'm sorry, not
Sounds
four,
good.
two.
Yeah.
I have to clean my glasses there. I saw the 4. It's 14:18 in my time zone. So at 14:25 in my time zone, we'll come back together and we'll start on the next idea, playing in the sandbox. Okay, a few comments to begin with on what we've done or what we've just completed. So for the diffusion, it was both recursive and iterative. We're going to do some things that are iterative but not recursive next. We had a grid, we defined the relationship once, we spread that out. A few ideas on how we could make this a more intelligent model. I'll ask you for suggestions. Do you see anything that we did by hand that was repetitive that could have been adjusted and would give us another variable in the model? Well, let me suggest that the temperature for the heaters could have been a slider bar control. And so we can actually make it more physically like a thermostat. Likewise, we could have an outside temperature that we could define this outside temperature rather than typing in the number 0. We could have a variable that represents the ambient outside temperature and make that the surrounding temperatures for everything that's going on out there. And again, we could make that a slider bar if we wanted to try different things. So this is obviously just a rudimentary part of the sandbox, but you can make it more complete if you would choose to do so. That would be up to you. Now that you've had your break, I want to make sure we have any questions or comments answered before we move on to system models. Okay. My intention is to take the diffusion model and the iteration, the 2 tabs, and I'll make that a shareable, I'll make that a link on the page so that you would have sort of a, if you go back to this talk later, you would have the ability of downloading it. Or no, we'll put it on the Google Doc. Okay, Aaron? Okay.
Yep, sounds good.
All right. So let me talk a little bit about the general concept of system models. What we're usually talking about with difference or differential equation models that are inherently iterative. They're not necessarily recursive, but they are iterative. What you're really talking about, at least at the simple level, is what's called the Euler model, which is simply what you have is equal to what you had plus what changed. Now, explicitly in this layout, in this format, we've already built a system model a few minutes ago. Can somebody suggest which system model, which model of the world we built that had this, what you have is equal to what you had plus what changed? We had the new time was equal to the old time plus the step. And every time we hit command equals or F9, step would be added to the old time, and then that value would become the new value of time. Then that value of time would become the old value of time. Step would be added to it, and then it would come over here. But there's lots of things in the world which could be solved iteratively, step by step by step. And a spreadsheet is a wonderful sandbox for teaching this type of thinking of row by row or column by column, step by step by step type thinking that goes through and enables you to figure out, without having to learn how to program a loop, without having to learn how to program an array, without having to learn to program a data structure, without having to learn to program a termination condition. Just row by row, define the new row as being the values from the old row plus the change, and now you have a new row. And we'll show how that works. If you're in physics, where you are, your new position is equal to the old position plus the change in the position. The new velocity is the old velocity, but plus the change in velocity, which is the acceleration. The new acceleration is equal to the old acceleration plus the jerk. The change in the acceleration is known as the jerk. The change in the velocity is known as the acceleration. The change in the position is known as the velocity. But each of these could be modeled, and we'll show you some examples today of what you have is equal to what you had plus what changed. And we'll do this row by row. We'll use variable names. We'll use new values being equal to the old values. And we'll try to use this idea that if you define the change in the system correctly once, then the whole model can be copied down and you don't have to do any more work. The tedious, repetitious part can be taken care of altogether. Okay. So let me go back to my spreadsheet here. And we're going to do a very, very simple population model as our kind of prototypical example. We could use money and interest. It's still late spring. We can talk about bunnies and bonification and the idea of also talking through equations in English while you're writing down symbols on your marker board or on your iPad or however you teach. So if we had some rabbits, and we could say the number of rabbits was changing over some change in time because a fraction of the rabbits were having bunnies. A fraction of the rabbits cause a change in the number of rabbits over a change in time.
And Bob, there's a little bit of a lag.
Okay.
So yeah, I don't know if the symbols are lining up with the words quite on time.
All right. So if I read this left to right, rabbits are changing over a change in time. The equal sign is pronounced because when you're going left to right in biology. The B, the lowercase b, stands for the birth fraction. That's the fraction of, the multiply sign is pronounced of in most cases in English. And the R is the number of rabbits. Now, if I just read this to my class, delta R over delta T equals B times R, it doesn't have any meaning, but the semantics are important. If you read it in the other direction, you could say fraction of the rabbits cause a change in the number of rabbits over some change in time. Now, if I multiply up by delta t, what I see is I can define the change in the number of rabbits as what I have here, which was the original rate of change. This is the rate of change, and this is the actual change. Again, I'll try to talk as slow as the delay may show up. If I expand the change in the number of rabbits as being the new rabbits minus the old rabbits, gives me the change in the number of rabbits then I could write this as the number of rabbits that are new. I'll put the old rabbits on the other side of the equation. And you can see that I've now transformed this into the form of what you have is equal to what you had plus what changed. So what looks like a differential equation, originally I've written it because I deal with lower level math students as a difference equation. The delta t could also be written as dt, or it could be the step size like we did before. But this thinking, when you start out with the rate, and you can understand it, that's what's going to be different between one model and the next. And we'll talk about a couple of different models of population. But the way this will work is we'll calculate the new number of rabbits on the line below where we've already had the old number of rabbits. Now, to build this up, to show you, I've done a lot of the typing for you. What I'd like you to do is you can go here in the model here. The first thing I'd like you to do is to save your iterative model, quit Excel, and then download the new model. If you don't do that, what you'll have to remember to do is when you open the new model, you'll have to go back to the calculation and remake it automatic and unmake it iterative. So while you're doing that, I'm going to do the same thing. I'm going to save this. And,
Bob, just so you know, we can't see your Excel model at the moment.
oh, okay. Well, all I'm doing is saving it. So, and then I just quit Excel. So now if you click on simple population, what should happen is this model should open and look like this. And when I say look like this, I need to share it as the Excel model that's open. Now let me explain how I built this template. On the left-hand side, I've typed the equations as you suggested, but instead of using a delta, I use the letter D. But can you see that these 4 lines are essentially what I wrote on my iPad. And what's in parentheses is the rate of change as we originally wrote it, B times R. And by using names, I've named this column G as R0. I've named the column H as R sub n. My model of time is going to go down this row, and the new time is the time from the previous row plus delta t. dt is the time step, which I'm making 1 day. I didn't hear that. Somebody have a question? Okay. R0 starts as the initial number of rabbits, which I called initial underline R, and I'm going to start with 2 rabbits. And then the way the old rabbits propagates is on the line where I calculate the new number of rabbits, I start by copying down what had been the old number of rabbits diagonally. And this alleviates the need to turn off automatic calculation because each row is separately calculated from its own set of numbers. Now, if I look at the actual formula, again, based on yesterday's example, some of you do not need these @ signs, and you may not even have them. If you don't have them, you'll find out very quickly if you need them. If you have them and don't need them, you'll find out very quickly. But what this is essentially saying is the new number of rabbits is the old number of rabbits plus the change in the number of rabbits, which is the rate times the time step, which gives you an amount. Let me get my zooming correct. Now, if you want to propagate this model in time, you would highlight the 3 rows of the model and copy down those 3 rows. And you'll notice that in every case, the old number of rabbits is diagonal, defined as the previous new rabbits. And the new number of rabbits depends upon the value of B, the value of dt, and in this row, the value of the old number of rabbits. Now, what you can observe, you could ask your students what they expect. Some students will say they expect the number of rabbits to increase. Some will actually tell you that they think it will be linear, especially if you only do the first few rows. What I'm going to do is clear these, and the students will look at the graph and say, well, it's not really changing very much, but if you look over here, it is changing. If you go up a few more time steps, they'll say that to them, it looks linear. But if you actually go down and do it, you can see that it's super nonlinear. In fact, it'll turn out to be exponential. And that comes from this original equation that the change in the number of rabbits over time is a fraction of the number of rabbits. If you've had calculus, you could say that the number of rabbits is proportional to the number of rabbits. The rate of change is proportional. And you know, in that case, it implies that if you were to divide by r, multiply by dt, and integrate, you would get an exponential. But you don't have to get an exponential mathematically, you can get it graphically.
With bacteria growth, we refer to that linear part because it's often what we're looking for as the linear phase of the exponential growth curve.
Right. And that's where Galileo went wrong. Galileo thought that forces were proportional to velocities, because when he did his experiments, he thought that the square of, he didn't recognize the quadratic nature of projectile motion. He thought it was linear. And for small values, it looks linear. I mean, one of the things that's really interesting is when you get these conundrums and the students go bonkers. For instance, suppose somebody said, like Galileo, that for most numbers, the square of a number is basically the number. You say that's crazy. Well, let's try it. What is 0 times 0? Anybody?
0,
What's 1 times 1?
1.
See, I've done 2 examples. And in every case, the square of the number was basically equal to the number. And for small values, the linear part, and what did you call it, the linear phase?
Linear phase.
Between 0 and 1, it's very hard to tell the difference between a linear model and a quadratic model. So, you know, trying to get the students to not only expect, but to keep going, you know, make it bigger, see what kinds of things that you can get going there. So let's talk about this model a little bit of where things are going. Obviously, one of the limitations of using Excel is when you're done, all you have are these columns of numbers. Next week, when we have an entire workshop on system modeling, it will also talk about system modeling software, which is much more visual, like a concept map. But it doesn't have to be. Now, if we came over here, the only thing that I have connected to a slider bar currently is the birth rate. Let me ask you, what would you expect this curve to do if I increase the number of rabbits that are born per time step? If the fraction of rabbits having a rabbit increases, what would you expect the total number of rabbits to do over time?
It increase. And your slope gets
Can you
sharper.
see the exponentials going up faster? Now, if I decrease the birth rate, this is what we call flattening out. And you can see you get a lot longer part that looks like it's in the now identified as linear phase of the situation. So let me get back to where we had this before. Now, we could do lots of different models, and it's all based on your ability to tell a story and convert it into a mathematical description of the change. So let me tell you some stories. And let's see if we can't see what that tells us is going on. First of all, what we've seen in this model, that when the rate is proportional to the number that you already have, we end up with something that's exponential. And again, my argument was that if you divide this by r and multiply this by dt and integrate both sides, you would end up getting an exponential. And you can see that that was actually the case. But let me tell you another story, or you tell me does in fact, in the real world, the number of rabbits just increase exponentially without limit? You'll notice that there's no death in this model. There's nothing negative in this model whatsoever.
Nope.
We just get more and more rabbits. What would be more realistic?
You're going to have a maximum because you have a death curve in there. You're also going to have limited resources.
And we often call that a carrying capacity. Does that sound familiar?
No, but
Okay. But what you called it was a maximum number. So the basic carrying capacity model is that if I want to describe the change in the number of rabbits, I still talk about the fact that some fraction of the rabbits are having bunnies. There is a birth rate, but there's also a factor that at the beginning starts out by not changing this at all. But as the number of rabbits approaches the maximum, if R is very small and the maximum is very large, in English, how would you describe the number of rabbits over the maximum? Is this a large number or a small number?
small.
So at the beginning, when there's a small number of rabbits, we might expect to still get what we had gotten when we multiply this by 1, and this R over M is so small, it's negligible compared to 1. But when the number of rabbits approaches the maximum, what does that ratio approach?
It approaches 1,
And what is 1 minus almost 1?
almost 0.
And if it was 0, we would know that the number of rabbits would end up being a constant.
Yes.
And then somehow there's a connection between one of these and the other. So if this is the rate, we would expect that if we graph that rate, that we would start out looking exponential, but eventually it would level off at some constant, the constant being the maximum number of rabbits that we put in there ourselves. So let's do that. Let's go back to our defining cell. And I'm going to mark this, put right here. So now instead of, let me attempt, I'll do this twice. So the rate that I'm going to put in here is going to be in parentheses B times the value of R0, or R, the letter O, that's when it stands for old, times 1 minus the old value of rabbits divided by the max. Now, the only thing I need to do is make sure that I called that variable max, but whatever I called it in the spreadsheet, I called it R max. So I'll go up here and change that to capital R little max. So that's the formula that I'm going to put in the first time step in the parentheses. Oh, I need another closed. What did I just do? I need to close my second parentheses. All right, and then I close that parentheses there. So I've got 1 minus the old value of rabbits divided by R max, and all of that is multiplied by B times R. So if I copied that and replaced this, you'll notice that it's almost 0. I mean, there's really no change when you begin because it's such a difference. Then if I double click this all the way down, then you see it changed every value to that formula. Now, if I go back and look at the graph, can you see that that graph is as we expected? It's going to start out exponential, then flatten out. If we changed the R max to 500, where will the flattening out take place? At 500. If we made it 1500, it would flatten out there. And again, this is where the question from yesterday, if we had a slider bar, a scroll bar, we could actually see it.
Didn't get that. Could you try again?
Computer thinks I want it to help me. So a carrying capacity has the artificial nature that you're actually putting in the number that you're telling the acre of rabbits that it's going to end up converging to. It doesn't really give you a reason why there's a carrying capacity. It just tells you that there is. But can you see that all we did was, once we built the basic model, we just replaced the expression for the rate of change, copy that down, and now we have the new model. Now there's another model of rabbit population, which is called the competition model, which basically says, if you're a rabbit and I'm a rabbit, and there's one blade of grass left, one of us gets it and the other one doesn't. And if that happens often enough, somebody's going to not make it into the next generation. If there's one drop of water left, one of them gets it, one of them doesn't. If the wolf is coming and there's one rock to hide behind, one of them gets it, the other doesn't. So whenever one rabbit interacts with one of the other rabbits, and I don't care if it's Flopsy or Mopsy and Flopsy, somebody doesn't make it into the next generation. That's called competition. And I can tell you the story of competition as I just did, but I can also tell you the story with some time lag we know because of the iPad by writing down an equation that represents the rate of change because my story involves competition. So let me tell you the story of competition, and I'm going to use symbols to represent my English words as I'm doing this. So what I'm going to say is rabbits are changing over time because some of the rabbits are having bunnies. Does that look familiar? However, a fraction of the time, when one rabbit interacts with one of the other rabbits. So if there are rabbits, there are R-1 other rabbits. And I don't care if it's Flopsy or Mopsy or Mopsy and Flopsy. Somebody doesn't make it into the next generation. So I have clearly birth and death in this model. This is a linear term, this is a quadratic term. And at some point, based upon the birth rate and the competition factor, these two terms are going to cancel. And the rate of change is going to go to 0. And at that point, it's going to level off. But I don't know where it's going to level off. I just know that at some point, when I have a linear growth and a quadratic change, that at some point, they're going to change. Any questions on my story or how I symbolically represented my story? Now C, here, let me pause after I ask the question. Any questions or comments or concerns on that? Now, can anybody give an explanation why for the value of B, for the birth rate, I started off with a fraction of a half? I basically said half of the rabbits are having bunnies.
Gender.
Gender. And the fact that not every rabbit survives being a bunny. But on a generation to generation iteration, you get about half a bunny growth per rabbit of your existing population. Now, on the second term, the value of C is going to be quite small because you have an R squared. So this might only be 1 out of 1,000 or 1 out of 2,000 or 1 out of 5,000 times when rabbits interact with other rabbits. As a result directly of that rabbit, somebody doesn't make it into the next generation. So some of my students think that when I talk about competition, I'm talking about these videos you see where kangaroos are fighting other kangaroos, or tigers are fighting other tigers, or rhinoceri are fighting other rhinoceri. But if I go back to my Excel model, and I'm going to label this carrying capacity. I'll have another model, which would be basically B times at R0, RO, minus comp. I have a variable I already called comp, times the old number of rabbits times the old number of rabbits minus 1, and I divide all of that by 2 because I don't care if it's Flopsy or Mopsy or Mopsy and Flopsy. So you get to teach a little bit of combinatorics when you're doing this. And if I take that whole expression and I replace the model, now I have the birth rate times the old number of rabbits minus the variable that's in my list called competition times R0, R sub the letter O, the old rabbits. So R times R minus 1 divided by 2 is the number of different ways that rabbits can interact with each other. And a fraction of those results in somebody not making it.
Bob, I think you might be missing @ signs on the
I am
order.
missing 2 @ signs. Thank you. Sometimes I let the computer whine. By the way, the symbol for whining is called spill. If you need it, if you're using it and you don't have the @ sign, it will try to take the entire column G and spill it into that one number. And it looks ugly and it's, so thank you for catching that. Let me go down here on my typed. Oops. Put the @ there, the @ there. And we'll call this competition. Now, if I go over here, right now my competition is 0. So all of this is 0 when I start out. Let me copy it down. And so what it should look like is it should look exponential because there is no competition. Now, if I make my competition 0.00001, it drops a little bit. If I make it a little bit bigger, it makes it a little bit bigger. If I make it 1 part in 1,000, it flattens out. So I don't know if you're noticing this, but by having a competition of 1 part in 1,000 with a birth rate of 2, I end up with a flat line of 1,000. If I double the competition, I get even fewer rabbits. It goes down to 500. Oh, that's too many zeros. If I make it smaller, I end up with a higher. So you could, again, if I was to instrument this with a scroll bar, you could see that as you increase the number of competitions, you get fewer rabbits that survive to the next generation. But the basic idea is what you have is equal to what you had plus what changed, line by line by line by line. And you can think through the early part of it to figure out what's going on. And the whole model comes down to putting something in these parentheses that represents the rate of change in your model and going between the description of what's happening, the hand waving version, the explanation of the version, and the mathematical representation of that can go right into the model. So what we often say is that competition can explain why there's a carrying capacity. A carrying capacity can explain why there's a certain amount of competition if you don't have enough resources to sustain a given population. And so the two are different explanations. And computationally, you can implement that model row by row by row by row in Excel. And you don't have to teach loops. You don't have to teach termination conditions. We didn't do any branching or conditional work in this particular model. We just deterministically calculated the next row based on the values of the previous row. Are there any questions on what we did? Now, if I go back to this model, instead of rabbits, I could have been talking about money. I make a certain investment, and instead of a birth rate, I could make this an interest rate for the growth of the money. I could have different parts of the model that instead of competition or carrying capacity, I could have taxes and fees that would take the money out of my bank account while I'm making deposits that would be putting money into the bank account. I could have more complicated models, and we'll talk about them if there's time, where I could do susceptible, infected, recovered, and each one would be a separate row. And I would calculate the new and old values of healthy and infected and recovered. But the basic idea is what you have is equal to what you had plus what changed. That's really the entire mathematical concept of what's going on with system modeling. Somebody asked, did I mean SEIR? I could. There's a whole cascading series of models that starts with susceptible infected, SI, susceptible infected recovered, susceptible exposed infected recovered, susceptible exposed infected relapsed recovered, and all of those could include death. I mean, a very healthy person could get hit by a car and they don't make it. They don't ever get the chance to get the disease. Infected people could die from the disease and they never get the chance to recover. Recovered people could have slower reflexes and could get hit by the same car. And so your model is built up. This is a good time to take a break. It's now, by coincidence, close to where we were an hour ago. I've got 3:13 or 15:13. So how about at 15:20, we come back and we'll finish the last hour with some agent modeling. Okay, we've got our last stretch here. I'm going to sort of describe a little bit about agent modeling. Again, in 2 weeks, when we do the agent modeling workshop, we'll be using software primarily. We'll actually use an Excel example similar to the one we're using today, but we'll use software that is designed to make it easy to introduce agent modeling to students. Next week, we're going to use software that makes it easier to see what a system model is and how the parts interact with each other. But the Excel sandbox experience, I think it's important because you don't need special software, but you do have to sort of understand these different parameterizations of things that are going on. Did anybody have any questions that came up during the So what we just did for system models was implement row by row, what you have is equal to what you had plus what changed. And if you can define the change correctly once and then copy it down, and then you can use controls. What I recommend that you do now so that we can start the agent-based model is we're going to go back to an iterative manual calculation. So I would recommend you save your population model and download what's called the Game of Life. And while we're doing that, so I'll describe characteristics of agent-based models. Typically in a system model, things happen at a certain rate. In an agent-based model, they happen with a certain probability. In a system model, you typically have equations that are then iterated. In agent-based models, you typically have rules that look like nested if-then-else statements, but you don't have as many equations as you have conditions that have to be iterated. In both, you could have boundary conditions. you can use different types of color to represent different types of agents. And agent-based models are a good environment to introduce parallel thinking and parallel computing. There are different algorithms for updating what happens from one time step to the next. You could update one agent at a time, and then that agent's new position, new condition, new temperature affects the other ones. And Gauss-Seidel is what we used in the thermal model, even though the Gauss-Seidel updating, which is you update one cell at a time, and that new value is then used to evaluate anything near it. In Jacobi, which will give you an example, you use new and old copies, and all the new values depend upon all the old values, and then you switch the two copies of your vector or matrices or things that are going on. So you want to have the game of life open. Let me open my copy and share it. Let me, oh, I stuck it in downloads. And then share game of life. Okay, let's see if you can recognize how many things that we've learned over 2 days that we're using in this model. On the left side, do you see that I've defined a start variable and an iteration variable that's actually a counter? I have a fill density that describes what fraction, if I were to do something random, what fraction of the cells would be filled. Whether or not I have torus or island boundary conditions and whether there's a delay. So the question I have is, we're going to explain this on the iPad, but is there anybody that's loaded this that doesn't have this all set to go? And again, if I go up to preferences or options, when you downloaded and open this file, it's automatically manual and iterations 1 because that's how I saved the model. You'll also notice that I made the squares really, really, really tiny. You'll also notice that the outside border is brown and the agents on the inside are either white or black, depending upon whether they're alive or dead. That's done through conditional formatting. So we use variable names, changing the grid size to make it more geometric, conditional formatting, and eventually you're going to see that we're using an incredibly nested if statement. Did anybody not load or was not able to load that? So the mathematician Conway, who was one of the first victims of the pandemic a year ago, developed this idea to look at whether or not you could have emergent behavior from very, very simple sets of rules. And let me describe to you so if you had a tic-tac-toe, not a 3x3 grid, all 8 of these values are your neighbors. We're not going to do just nearest neighbors like we did before with the diffusion. We're going to use all 8 neighbors. And here's the way the game works. Step by step, every single cell in the matrix. Every single cell in the world is evaluated. And if you have 0 neighbors, you die from loneliness. If you have 1 neighbor, you die from loneliness. If you have 2 neighbors, if you're dead, you stay. If you're alive, you stay. Whatever your condition was, if you were a white cell, you stay a white cell. If you're a black cell, you stay a black cell. But, you know, if you're going through there, if you have 3 neighbors, you're alive. If you were alive, you stay alive. If you were dead, you become alive. And greater than or equal to 4, you run out of resources and you're dead. So let's think of a couple of simple examples. I'll use the fill-in to represent me. If I had no neighbors on the next iteration, what would happen to this filled-in square? Anybody push down your microphone and...
It would die.
So this will become a clear cell the next time. If you had 1 neighbor, and let's say this was an isolated thing, each of these cells has 1 neighbor. So what will happen to both of these cells on the next iteration?
They'll become clear.
Okay. What if I had 3? Well, the center cell has 2 neighbors. So the center cell stays alive. What happens to the top cell that only has 1 neighbor?
Goes clear.
What about the bottom cell that has 1 neighbor?
Also clear.
What about this corner cell that has 2 neighbors?
Stays.
It stays, so it stays clear. So all 4 of these stay clear. What about this side cell that has 1, 2, 3 neighbors?
Becomes blue.
So what would happen is on the next iteration, it would switch to looking like this. And then on the next iteration, it would switch back to being vertical. So these 9 cells would flip between being 3 vertical and 3 horizontal. And there are more complicated models on the same thing, but what's going to happen here, let's just run it to see if you can tell. I'm going to start. And then I'm going to hold down Command equals. One of my students says this reminds them of the old blinking lights at the beginning of the Rocky and Bullwinkle show. So let me stop and point out that look at this 3, 3, 3. Every time I hit it, do you see how they're flipping back and forth?
Yes.
Here's one in the middle, back and forth. This is a little island. This is a rock. These are 4 cells linked together. What happens to those 4 cells? Oh, now somebody's hit it. So the idea is that this is a mathematical model that some people have talked about, emergent life, emergent artificial behavior that comes out of a very simple set of rules. If you have 1 or no neighbors, you die. If you were dead, you stay dead. If you have 2 neighbors, if you were dead, you stay dead. If you're alive, you stay alive. 3 neighbors, no matter whether you were alive or dead, you're now alive. 4 or more neighbors, you're dead. Now, the way this works in Excel is you take advantage of a very special feature in which Excel calculates starting in the top cell and goes over and then goes down. So in this particular model, everything on the top row is evaluated between the next row and the next row and the next row. But what they're actually doing is they're simply setting themselves equal to cells that are down here at the compute level. And each cell here is this insanely nested set of if statements. So the first cell says if starts equal to 2, then I randomize myself. If start is equal to 0, I go down another 100 rows and I set myself equal to whatever I had set up there on the level. If I'm neither 0 or if I'm neither 2, which is random start, or 0, which is fixed start, then if I'm not delaying, then I come over here and I add up and say, if the sum of all 8 of my neighbors is 2, then if I was a 1, I stay a 1, otherwise I stay a 0. But if the sum of my numbers is 3, then I automatically become a 1. And if it's anything else, 4 or higher, then I'm a 0. So that's why I called this. So let's see if this works. If start's equal to 0 and I hit 1, command equals, then I'm basically setting myself equal to this initial condition, which I had worked out earlier. You know, if I come up here and set something else. So I'm going to put a traffic light, a blinker right here at the top. And watch what happens if I hit command equals again. Do you see my traffic light showed up? And then if I hit 1, it flips the other way. It goes up, comes down, goes up, comes down, goes up, comes down. If I set it equal to 2, it randomly fills the box with 41% values are on. If I made it 100%, if I made it 0, they're all off. What do you think is going to happen if I make it 80%? If I take one step, what would you predict this would probably look like? All right, so I hit start equals 1. Almost everybody dies because if I have a probability of 80%, then almost all of the on cells are next to 4 or more on cells. And so on the very next step, most of them disappear. And on the next step, and after a very few, so that's overpopulation. If you make this 40%, and you populate it with a 40%, then even though it was completely random, see if you can tell that there are actually animated objects that appear to be moving in some particular way that came out of a completely random start. Now, the border is either a torus, which means it's like a donut. The left side is connected to the right side. The top is connected to the bottom. So that means that things could actually cross over and go from one side of the model to the other. And if they go out the bottom, they come in the top. Or you can make this 0, in which case when things hit the edge of the wall, they just hit the edge of the wall. So you can have simulations that involve some degree of randomness, some degree of stochastic behavior, some degree of deterministic behavior. And a lot of it just depends on how you do the setup. And if you randomly give it another start, you can get a different value. So Igor was saying when he was a kid, he used to play this with paper and pencil. So let me ask you, Igor, did it take you a while to do that?
Yeah, it was super tedious, took forever, but I had no computer, I had no choice, and I had a lot of fun doing that.
And again, people do it with coin flips and they have two-sided coins. And then you either take the coin off the board or you put a coin on the board. And you just, but it's once you set up the conditions, everything is deterministic.
I learned about this game in Martin Gardner's books, and he gave some interesting constructions like guns that shoot flyers, and so some
Yes.
interesting stable constructions. So yeah,
And
lots of
and
interesting-
Aaron, I'm sure, can put up the link to the Interactivate Game of Life. Is that possible to find that quickly and put in Life Light? We have web-based versions that were written in JavaScript that allow you to do Methuselahs and guns and things. But let me give you an example. On this screen here, this object looks like 1 diagonal and then 3 on the bottom. This is called a slider or a glider. And the reason it is, watch what happens next to this object right here. Do you see it move? And now it's back to its original shape. And now it moves and it's back. Now it hits something. But you'll see these gliders forming naturally and then also coming back. So here's a glider here. Watch this one. You see how it's like a worm swiveling and sidling? Now it hits something, so it's no longer a glider. But the idea is you have a set of rules. Those set of rules are implemented. And the parallelism is that every square here merely sets itself equal to what it would be farther down 100 rows. Every square here looks up 100 rows to calculate what its neighbors are, and then sets its value to 1 or 0 based upon what that is. So it's completely parallel. There's no interaction between the next available cell. If you were to do that, you get very different rules altogether. This is called Jacobi updating, in which you use 2 copies of the same matrix to go back and forth. Let me see if I can apply a conditional formatting rule. No, it won't let me because it's already been done. I think part of it is the share. Aaron, can you tell me what you mean by menu system is broken?
Yeah, if you go to the link I pasted in the chat, there's within the activity, there's menus that you can click, for example, the pattern list in the game setup, and you can click on the items, but the styling is kind of messed up.
Okay. We may play with that if there's time at the end. Okay, but again, you know, there are different sets of rules that you can do to sort of figure out where things are going. Right, so I could set up so what I'm going to do is to try to copy all the way across, then copy all the way down. That should give me a clear screen. So now what I'm going to do is I'm going to build a glider. This is an individual object called a glider. And I'm trying to do it so that it'll simplify. So do you see I have one glider? Now you can watch what that glider does. And there's no other objects to interact with. So all it's going to do is, now where's it going to go when it hits the wall? It's going to come in from another point because the boundary conditions are wrapped. And if I go down here and create another slider, except I do it with a different orientation, can you predict which way it's going to slide? So now I've got one pointing one way and one pointing the other. What do you expect would happen? Do you see they're going in opposite directions? But they maintain their overall periodic shape. Now, if they ever hit each other, they could annihilate each other. Now, if I change the boundary conditions so that the walls are actually hard, then one of the things you can observe is that a glider hitting a wall that is not wrapped turns into a rock. Anyway, there's lots of things you can do, but the key thing is rules-based models can be played with, can be built, can be explored in Excel, in a spreadsheet, using the various atomic or molecular pieces we learned, making it look like a grid, using color formatting to distinguish between a 0 and a 1, looking at nested if statements, copying, taking advantage of the fact that Excel calculates left to right from the top down. So you can actually have two copies. So once you hit Command equals or F9, it calculates through the spreadsheet once, and then it comes down and does it again. So the top sets it's equal to the middle calculates from the top, and then it repeats that cycle over and over. Now I want to talk about some resources that we have. I didn't know how much time we'd have left, so I made this slide. On the Shodor-Nixie thing, there are all kinds of examples that you could look at. There's a dosing model, an SIR with scroll bars, sequence analysis, Laplace equations. I mean, there are all sorts of things that are similar to what we've done. One of our first graduates of one of our first workshops was a community college teacher in Maryland named Scott Sinex, and he decided to build hundreds of these examples that he calls Excelits. They're little interactive spreadsheets that involve chemical or math science or astrophysics and mathematical modeling. But what he's done recently is he's dedicated himself to modifying things that could be done with Google Sheets. And in all of those things, you have to make your own, when you click on something, you can make your own copy of it and get some type of interactive things that are going on there. But he's been working on a number of his examples, like modeling population growth, you know, for different types of things. So data analysis, this probably should look pretty similar to what you've had before. Population growth models. One of the things that's frustrating is you don't really have a scroll bar, but you can see from his thing, you've got limited. But Scott has a tremendous amount of stuff that's there, and I would recommend that you take a look at that set of materials. I promised yesterday that, and again, I marked this temporary home because at some point I've got to hide this because otherwise the students will know. But when I start the course, this page is essentially blank except for one or two resources and some rules. There's a link to the syllabus. And what we're going to do and how we're going to do it, what we're going to understand, how the course is graded. And then different discussion resources. We have a list of vocabulary terms used in the sciences, like necessary, sufficient, consistent, conclusive, correlation, causality. Because it's a liberal arts school, I put up a link to St. Thomas Aquinas talking about the ordering of the sciences and how every science has its own method and its own object. How computers are used in scientific investigations. Basic ideas of statistical measurements. A link to the fractal microscope. Different types of n-body explorations, different tutorials, some assignments, and the 8 labs. And then there's a 3-week project that the students are expected to do, which counts a fifth of their 20% of their final grade. So some people mentioned they wanted to see a copy of that. So, and again, at some point, I've got very smart students who learn how to hack servers, and I'm going to probably hide those materials so the students don't see the whole course. I want it to unfold for them as the semester goes on. So we start with a fairly blank page, but then I edit the page. And I do that basically because I'm selfish, because the Moodle implementation kept changing. And I didn't want to have to learn the Moodle 3 times in the same year. So I just made my own flat HTML course management system for things that are going on there.
So I have a naive question. So obviously this material needs sometimes for anyone to go through. So for my students, you know, it will take me some time to kind of go through these materials and kind of pick whatever I need for
Right.
my specific teachings. So
Right. If
how
I,
long?
if
How
I-
long? Yeah.
the new semester starts September 2nd, probably around the middle of July, I will change this URL for what happened last semester to something else, and we'll send that to anybody who's on this workshop.
Okay, understood. That makes sense. Thank you so much.
But at some point, you know, I'm not going to reinvent the course. The new course will not look like what we did last year. The examples will be different. A lot of it depends on what student. It's a gen ed course. So 2 years ago, I had a lot of accounting and economics students in the class, and we did more accounting and economics examples 2 years ago. Last year, I didn't have any, but I had more biology and chemistry and physics students. So I put that stuff in. So the examples that we actually end up is at the beginning of the semester, we survey the students and I understand what their interests are and what they'd like to learn, what they'd want to model, what they'd like to study, and then we put that all together. Now, version differences are real and software changes. I want to give you one example of this just to make sure you don't think I'm bad-mouthing Microsoft. Are you all familiar with Python?
Yes.
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 Okay. So here is an older version of Python in which I'm going to do the calculation we did before. And what would you expect to get?
Zero.
Or do you remember we actually got non-zero?
Yeah, I remember that too. Yeah.
But on the 2.4 version of Python, you got zero. But the reason you got zero was because it was doing integer division and every piece of the problem was zero. But if you use Python 3 and you do the same calculation, I gotta hit this. Then you get the non-zero. So between Python 2 and Python 3, the default syntax for integer arithmetic was in fact floating arithmetic. So you may develop a set of materials for your students in Excel or a spreadsheet, and somebody changes how that piece of software works. And that's to be expected. And you just have to be kind of aware, you know, where I was shocked. It was like last year when Wofford updated everybody's copy of Excel, all the stuff I had prepared that did not have that little @ sign, suddenly I was getting spill errors. And I didn't know what a spill error was. And then you do some Googling and you find out that the new version of Excel requires this @ sign to pick off the row value of a column that's been named. So that you go back and you change all your models to take that into account. Then you have half your students that still have the old version of Excel. So you have to have two different versions of things going on all the time. It's a challenge, but it's worth it. The idea of Excel as a sandbox, I think, is proving itself and has for quite a while. You can teach the concepts of programming before you teach the detailed syntax of for loops, while loops, if then else. If then else is in Excel. You know, you can teach the conditioning, the boundary conditions, polling, counting, sword fights, dragons. I mean, it's an exciting group of things that you can teach in Excel. And I hope over the last 2 days, I've shown you enough different examples. If you go over that list from the Nixie Shodor page and you want to have some explanation of what's going on in the examples, just send me an email and we can set up an independent Zoom session for follow-up. I sort of owe it to you to be able to answer your questions, I feel.
Indeed, that would be greatly appreciated. Thank you so much for the opportunity. Probably will do that. Yes, thank you.
Okay. So generally for everybody, we've got about a minute before it's 4 o'clock. I'll stick around for any questions, comments, or concerns. But just let us know what we can do to help.
Yeah, and I'll mention we do have a few surveys. There's one from Exceed and one from Nixie. They're both post-workshop surveys. There's also a daily survey for today. So the daily survey will ask you specific things about what we did today. The post-workshop survey is more of a looking from a more high level at the last 2 days as a whole. And so if you could find those on the Google Doc and do those, I'll also send a reminder over email, and we'll be posting the video for today, just as we did yesterday's video. There are some other links in the Google Doc for additional opportunities that are available through Exceed and other organizations. And there is still time to sign up for next week's workshop on system modeling and the workshop the week after that on agent modeling. So the system modeling workshop registration will close this Friday, and then the agent modeling workshop will close a week from Friday. So please get in touch if you have any questions about any of that. And thank you all again for your attention and your participation. And
In the chat window, I just put a link to what we call Life Light, which does have a working menu system. You can do the individual glider guns and Methuselah and single pixel or other things. I don't know why the life one isn't working. Okay, so we'll put up worked on versions of some of the models in the Google Doc. We'll have a link to those. And then if there's anything else that we can do, let us know.